have something for everybody here, a little bit for geochemists, a little bit for geophysicists. We're first going to talk about melt inclusions. There's nothing more important to measure in an active volcano than the melt inclusion. I have a little movie here just so everyone knows what a melt inclusion is. This is an olivine crystal. This is a micro CT scan. And we'll look inside and you'll see droplets of melt that have been trapped inside the olivine and therefore represent liquids, which are very helpful to model thermodynamically. We know that sometimes they have more primitive compositions. These are melt inclusions dancing around each other. The blue bubbles in them I'll talk about later as well. But they're liquids. They vary in composition, sometimes more than the bulk rocks. We can use them to understand pressure and temperature and viscosity, important things for how volcanoes erupt. They also, of course, preserve the volatiles because they're kept under pressure. And so they're the main ways we know water, CO2, sulfur, the degassing path, compressibility if you're trying to model deformation, or the gas composition if you're trying to model gas, or the eruption dynamics. So, all right, just melt inclusions. That's why so many of us are so excited about them. So I'm advertising a melt inclusion data set that Dan Rasmussen and I and some other, mostly it was Dan and I, put together 10,000 melt inclusions and downloadable from Earth Chem. We focused on subduction zones. So these are global subduction zones, continental rifts. There are other databases for ocean islands. We went to a lot of work. Dan and I spent the pandemic on the couch doing this, and we literally went through every paper. We fixed all the errors in GeoRock. We reproduced the figures in the paper. We matched the melt inclusions to the host, to the whole rocks, which are never done. We have all the major and trace elements. This is why it's an expert database, because we have vetted it. We've gotten rid of the errors, and we've matched up melt inclusions to their bulk rock. And we've inserted things like ferric ferrous if you need to know FO2. Yeah, in some cases we contacted authors. So just a few slides. Here's sulfur, 10,000 sulfur measurements from ARCs, huge amount of variability. I'm showing you the Aleutians, most of the Aleutian data set, one of the Aleutian data sets in orange. And so you can see there's a huge heterogeneity in sulfur at low silica. So that would be primary differences in each volcano. And the Aleutians covers most of the global range. So it's a great place to ask the question of why do some volcanoes have more sulfur than others? And then I just threw on there for fun Mount Spur, because we're also interested in Spur. These are unpublished data from Mindy's thesis. So just want to make you aware of that. These are some AVO samples that I'm not sure who gave them to us, but they wanted us to measure the last eruption of Spur. So happy to highlight those. And then, of course, the initial sulfur content will determine, along with water and FO2, as Echo showed, through sulfur X, where sulfur is going to degas as magma rises. And that's clearly important to the gas data that we measure prior to eruptions. Water is super important. Here's all the water data. Here's the Aleutians, huge variation in water from volcano to volcano. There's Mount Spur. And water is important because we've shown that it relates to geophysically determined magma storage regions, higher water, deeper storage regions. So water is clearly playing a role or reflected in magma stalling as well as eruption dynamics. The CO2 in the database is garbage. It's not our fault. It's just, it has to all be redone because most people measured the glass without the bubble. And once you rehomogenize the bubble, the CO2 changes dramatically. And so look at Daniel Lee's poster. I'm showing it here. For Okmok, all the prior data were below detection limit for CO2. And after Daniel homogenized them, now they're thousands of parts per million. That requires stalling at 15 kilometers depth, which is by the way where the seismic swarm was. So the CO2 all has to be redone, unfortunately. We only did up to 2019 because this was our pandemic project, and there's still been a lot of data since then. Most of it, though, I think are people in this room who are actively working on different volcanoes. And so should we redo the compilation? Should we just do it for the Aleutians? Should we crowdsource it? Should we be talking to each other? I think there's a lot of interest, right? And we should be Then talking to geophysicists about what we're finding. So I'm throwing that out there for discussion. Okay, now for something completely different. This is another hat that I wear. What sediments are getting subducted along the Aleutians? This is important for subduction recycling, what comes out of volcanoes. It's important for fault and earthquake dynamics. I forgot to put the attributions here. The beautiful historic diagram is David Scholl's 1974 monograph looking at sediments from east to west along the Aleutian Trench. And that's been reproduced multiple times over multiple decades in all of these other figures. That's been the primary data for understanding sediment subduction flux along strike. And so we've recently revisited this because there's a ton of new ODP data. There's a ton of new multi-channel seismic data that should be incorporated because there's huge variations in the sediment flux. And a preliminary version of that was published in Taryn Lopez's really nice paper on carbon variations along the arc. And we used our new sediment flux calculations from east to west along the Aleutians to estimate the carbon isotope variation. And she incorporated that in her nice paper. And there's a preliminary version, the supplement, if you want to grab it. Subsequently, we've actually worried about the décollement and what gets scraped off versus what goes down. And so I'm showing you along strike in those blue bars. Those are estimates from multi-channel seismic studies of what actually gets under thrust. So that's probably the most relevant to what gets subducted. So we've turned that into a long strike sediment thickness, and you can choose what you want. The incoming sediment, the underthrust sediment, that's probably the best to use, the trench fill, and then David Scholl's estimate. So we've down scaled the sediment flux. And of course, the interesting thing about the Alaska-Aleutian system is that there's a big pile of sediment way out in the middle of the arc because it's been sluiced down that topographic gradient, and then the sediment's dammed by the amyloid zone. And so there's a large amount of sediment that's subducting in the central Aleutians, and that hasn't changed from David Scholl's really important insights. It may have to do with where the big earthquakes are or where creeping is. And then the main point is here, so we have done the work of estimating at a granular level along the trench every 10 kilometers, how much sediment is subducting, what the convergence rate is, and how it projects to each volcano. So if that's of use to you, this is getting published. We're almost done with the paper. I actually have this for every subduction zone. So there's a master table: trench distance, sediment thickness, trench normal convergence rate. And then we were hanging carbon off of that. But if you wanted to look at water or barium or sulfur, this is the primary mass flux data set that you would hang whatever element you want on it. And so I'm very happy to work with anybody on this and share this table even before we publish it, and happy to take questions and discuss.
Is that tied to the best estimate of the incoming sediment composition?
That's what you would have to hang on to. Okay, so that's again, we've done that for carbon. We're doing it for water. They seem like a good place to start. You know, my earlier work was like one average for the entire trench. Okay, so we're trying to look at this at a granular level. And so you would have to look at different ODP cores, maybe make your own measurements. But again, I'd be happy to guide that effort. That's the point. And that this is the primary data to hang that off of, is the mass flux.
And if we wanted to hang our hats off of that, are there samples that you have in your possession that we could measure the same samples, or would we have to go through?
Oh my God, no, don't. I have tons of samples.
Okay.
And I have donated them to dozens of people who want to measure every weird isotope system. But yes, if you want to measure sulfur or something, we've been working on that, but happy to share anything that I have. Yep.
Question about I love the expert data set compilations. There's something that I know we're wanting to work on more too. One thing I was curious about, did you and Dan just like build a big table where you just lined up, here's the whole rock data, here's some collision data, or did you try to think about like that really sticky problem of how to actually like link those different data sets as like data sets in a more database.
It's
type
not
of-
relational, it's a giant spreadsheet.
And it's
Sorry.
just a hard problem.
That was our project. We just wanted to make it all coherent. And I'd really invite if someone else want to do a bigger job, but it's still pretty bespoke, right? The data sets, and they're in different publications and different databases. So we really just wanted to make a big spreadsheet. So it's all together as a start.
Yeah, actually, it's a question for your morning presentation. If we have 1 carat magma, it might take a few 100,000 years to actually finally exhaust itself. Where does it hang out?
Probably at the Moho, I don't know, or in the, it's where I'd hang out. You know, wherever those DLPs are, right? I mean, there's kind of magma being supplied and there, I mean, it's from the mantle by definition. We don't see necessarily big blobs of magma, but these are not large volumes, if you think about what we're talking about. It's a good question. I mean,
Yeah,
Jeff may have some input, or people who've thought about what the mantle, you know, velocity structure, or how bright the Moho is.
Is it possible for a problem that you could have 2 melts that are generated, say, 10,000 years apart, that would actually have the same chemical composition if they came from the same place?
But we'd see the thorium isotopes vary as you, and the uranium excess disequilibrium is created at the slab. And so if the slab were creating one and then 10,000 years another, and they were exactly the same, chemically they'd be the same, but the uranium isotopes would be different. So but we need more of these studies. I mean, it's something that would be really cool to look at. That's just for seed one, shows 1 ingrowth. Yeah.
Oh,
Are we okay still? You have stuff to talk about, okay.
I was
One more.
The mass flux estimates on a volcano basis, like suggest for global data sets. And for carbon, is it like arc wide or is it per volcano?
It's per volcano, but you can do like some product if you want the whole arc.
Oh, no,
Yeah, we have arc averages for every,
Okay. I'm interested, single.
we actually have this for every volcano. That was the point. If you say, what's feeding Cleveland? We have a line. So we've done this at the volcano level where we projected, you know, what's subducting at Cleveland. I mean, it assumes steady state. Yeah, it's at a volcano level. That was the point.
Well, thank you so much,
Yeah.
Sherry. That's a good idea.